Hello, everyone. Welcome, and thank you for joining us today. I am Cody Wen, the South Central Climate Adaptation Science Center's Operation Assistant, and I would like to introduce Dr. Samuel Sandoval Solis, who is an Associate Professor and Professor in Corporative Extension at the University of California at Davis, with expertise in water resources planning and management. He is the founding member of the Water Management Lab and co-host of Water Talk podcast. He works among scientists, engineers, environmentalists, system operators, and decision makers to design strategies that balance human and environmental needs for water resources through technical, practical, and science-based solutions that are socially and environmentally responsible. Dr. Sandoval received his BS in civil engineering and his MS in hydraulics from the National Polytechnic Institute in Mexico, and his PhD in environmental and water resources from the University of Texas at Austin. His connections in Mexico have allowed him easier access to information that other people in the USA haven't had. Today, Dr. Sandoval will introduce the natural and regulated flow regime of the Rio Grande Rio Bravo, explore periods of drought and water abundance, describe how the regulated system is currently in a sustained drought, and present some potential strategies and solutions for improving the water resources management in the basin. The South Central Climate Adaptation Science Center provided funding for the research he is going to present on today. Welcome, Dr. Sandoval.
Cody, thanks a lot, and thanks everyone for coming here. Thanks also for the audience that will be seeing this later. So, okay, so we have had a project with the South Central Climate Change and Adaptation Center for a Climate Adaptation Science Center for now, I think 3 years, almost 4 years. And to me, it's been definitely a pleasure to work with the center. Let's go ahead and tell you what we've been doing or what we're going to be talking today. I'm going to give you an outline of what are the things that we've been of the project. Then we'll talk about the natural water availability on the basin. We will understand drought patterns, flooding patterns. We're going to be talking about hydrologic resiliency, and then at the end, I'll provide some next steps. As I was mentioning, Cody, offline, this is the first time that I am presenting this, so please remember that there might be some hiccups there, but very excited to share with you this novel research. One other thing, very important. So this research could not have been done without the help of and actually the leadership of Laura, Ramon, Grace, and others that have been part of the Water Management Lab, other colleagues that have been part of the Water Management Lab. Okay, so the project was relatively simple. So the Rio Grande is a basin that either it doesn't have any water or has all the water in the world. So we will try to characterize this doesn't have any water, these drought periods, and also these water abundance periods. And we'll try to do it for a period of hydrologic analysis of 110 years. The proposal was in fact actually quite simple. So what we proposed was to estimate the water availability. So what were the natural flows in the basin for 110 years? I think the main, the biggest challenge that we had is that we proposed to do this daily. So do daily natural stream flows from January 1st, 1900, all the way to December 31st, 2010. Yeah, I get, most of my white hair in here, it was because of estimating those natural flows. After that, we decided with this data to analyze and do some flood analysis to estimate how the timing magnitude and frequency have changed, and in that way characterize floods, and also how to characterize droughts and compare when droughts occur naturally and how the current flow relates to those natural flood events. So when we had these natural swings of wet periods and flood periods in the basin, and how the current stream flow relates to those periods. I think in this case, a spoiler alert. So basically the basin has been in a perennial drought since the last 80, 90 years. Finally, provide some adaptation strategies. This is when we're planning to submit all of these deliverables and some of the progress of that work. Anyway, so we think that a lot of this information later will be used for develop environmental conservation and restoration policies. We will provide some key concepts of water management strategies. We think that this 110-year daily natural flow database will be the foundation for many other students to come, and also to characterize droughts and floods. For the research questions, you're going to see that we will be talking about strategies for resilience. Okay, so here we go. So we wanted to estimate the natural water availability. We proposed that we will estimate it in these 5 control points. I'm happy to report that now we have natural stream flow data for these points and for many other. Some in the Rio Conchos, 8 along the Pecos, 4 tributaries in the Salado, Álamo, San Juan, Pecos, Devils, Alamito, Terlingua, San Felipe, and Pinto Creek. Alamito, Terlingua, San Felipe, and Pinto Creek. So we have natural data for those. What we did, well, basically we collect all the available data that we had, and in some cases it was yearly, in some cases it was monthly, in some cases it was daily. And then once we have that information, first try to complete the time series data analysis, and we may have completed yearly, monthly, and then disaggregated daily. It was an important amount of work. We fill a lot of the data. Sometimes we use a Markov model. Sometimes for disaggregation, we use fractal multifractal. In terms of filling the data, we pull all the tricks out of the bag of hydrologist hat. From QPPQ, so estimating flow based on flow duration curves, regressions, mass balances. We pull all the areas, area ratios, a lot of tricks on the back. We were able not only to estimate natural flows, but also we estimated observed flows for 110 years throughout the basin. In most of the cases, we did a simple mass balance. So basically, we estimated diversions, return flows, change of reservoir, and based on this, we estimated incremental flows. These incremental flows were used with the natural flow estimation upstream to estimate natural flows as we were moving downstream. We'll report this or we will document this. So yeah, we will be very happy to share how we did it. I think what Cody was mentioning, yeah, some of these cases we were able to get the information from both sides of the country to actually estimate natural flows for 110 years. Okay, so some of the results, I mean, many of you have seen these graphs. So this is the natural flow of the Rio Grande, and as you can see at the end, it will be about 11 cubic kilometers. We know that now the river, that it is the red line. So in some cases there is no water. and in some cases, a lot of water is taken out from the river. You can see a lot of those here. And at the end, we have this outflow that instead of being 11 cubic kilometers is only 0.78 cubic kilometers. Now, what are the, this is how the river now looks like. In this area, the river, the Rio Grande used to have a snow melt signature. And now it is just a flat line. There is almost no water running, flowing in here. In the Rio Conchos, we have this kind of monsoonal or hurricane-driven signature. And now, I mean, most of that water is stored and used for agriculture in the Rio Conchos Basin. So below here, if there is no water coming from upstream or coming from the tributary, yeah, the flow regime is very, very diminished. So that's how we have in here. Naturally, the river will preserve a snow melt hump, and also will have this monsoon-driven, hurricane-driven signature. So it was a bimodal river. I think this was very nice. It was a river where you will be able to find in the middle of the West Texan desert cold water. It was a very magical river. And this will be below Amistad. This is below Falcon. And this is at the outlet. And as you can see at the outlet, out of those 11 cubic kilometers and all this variability, and it's still preserving the snowmelt signature and the hurricane signature throughout the basin, now it is a flat line. It rarely is any water escape out of the basin. Now, this is actually the results. So what I'm going to show you are the results of how does the river look like? So what you're gonna be seeing here, this is Ojinaga, Conchos below Ojinaga. So this is Ojinaga, Conchos below Ojinaga. Then we're gonna have Foster, Amistad Flow, Laredo, and Anzalduas. And this is somewhere here is Foster, Amistad, Laredo is somewhere here. And we have Anzalduas all the way to till the end. This is what you're seeing here is the natural flow, is how the flow was going from upstream to downstream. So each of these, the x-axis is the natural year, then the days, the day of the year. And that will go from 1 to 365. What you're seeing here is the flows as they are going from above Ojinaga and the annual volume on that year through the volume all the way to Anzalduas. So, yep. So you can see that naturally the river, so you can see that above Ojinaga, it still have this hump. This is the Rio Conchos. And you can see that once it passing below Ojinaga, all the way to Anzalduas, so from upstream to downstream, the river still have this snow melt event. In this case, the river also, as you can see here now, because of the Concho signature, that orange line, it will have the quintessential bimodal snow melt and a hurricane driven. This is super cool. I mean, we can go all the way to 1900s and see what was the behavior throughout these different control points naturally in the basin. So why is this important? We talked about always actionable science. So in this case, it is very important because this can help you out to estimate how much water was available in these years, how water was being produced throughout the basin. And it can also tell you how, if we estimated also the regulated portion of it, what was the impact of regulation how much water has been diverted in the basin. So, oh, sorry. So let's go here. So basically here I will select 1915. And what you're gonna be seeing is, once again, the different hydrographs tells you how much water was going down from upstream to downstream. 1920, 1917, it was one of the years with the largest flood event on the basin. Oh, 1920, we have a quintessential snow melt and rain. Here, this is only for below Ojinaga. You will see what was the estimated observed flow and what was the natural flow daily. Whew. This was a lot of work, like truly a lot of work. Anyway, so not only we did this for, so this is the summary of all the data that we have, in this case along the river corridor. We also did something extremely similar for the Rio Pecos. So what you're gonna be seeing here is all the different, the flow, the natural and the regulated flow regime, in this case at control point 1, above Sumner Dam. And you can see that we have the same data from, that one is 1993, and we can go all the way back to 1904. And of course, this data later will make sure we'll make it available. This is data that it will go from above Sumner, Artesia, Dam Site 3, Dark Canyon, Pierce Canyon, Red Bluff, and here in Pierce Canyon is the so-called state line. A lot of this information in terms also of actionable science can help understand what is the water availability and how the water availability has been reduced in the Pecos River between New Mexico and Texas. And why is this important? Because we have the Pecos River Compact, and that will help. This data can inform if the current level of water sharing is adequate, and also the amount of diversions that are occurring here. So anyway, so we have those two. If we didn't have enough on our plate, so these two, we've been double checking our numbers. If any one of you know me, you will know that I double check my numbers like twice or three times. Even though I do some of the math, I'll see if there is evidence that I can use, so I can see if my calculations or the calculations that we have done are accurate. In this case, I have been able to compare this, which is from 1900 to 1943, the Water Management Lab numbers, and that with a report that it was authored by Oribe. And basically what this person did, this former Minister of Agriculture and Water, compare our estimates with an estimate that has been highly cited and used for comparison. So in the Rio Conchos, we are there. In the Las Vacas, San Diego, San Rodrigo, Escondido, you can see that we're a little bit below. So it will be these ones here. In Salado, you can see that we are a little bit above. If we add these three Mexican affluents or Mexican tributaries, you can see that this is estimated when the treaty was signed. This is our estimate. So not perfectly on top of it, but quite there. Alamo, San Juan. So this is Alamo and this is San Juan. And basically it is about this much. We estimate a little bit more. The 50% incremental flow, so these gains, it were estimated about this much. We underestimated, but in total, the water calculated for Mexico is pretty close there. We think that, I mean, we're confident of our numbers. Now, on the US part of the Rio Grande Bravo, what you can see is that in Alamito and Terlingua, so these two, we have similar numbers. In Manantiales, in the good enough springs that are underneath Amistad Dam, we are kind of there. Devils, San Felipe and Pinto Creek, which are Devils, San Felipe and Pinto Creek, we are close enough. The main difference is that Oribe, or in this study, they estimated about 1,348 million cubic meters of water from the Pecos. We took a closer look for more than a year and a half of the data that we estimated, and we believe it's about half, or we believe it's about 60%, or our calculation shows that it's 60% of what it was estimated on that time. This is a huge, or this is a very, very important for many different reasons. So one is that, I mean, it was overestimated, definitely. We've done it, we've done our calculations 4 times, it was overestimated. This also change, or we can change how this water, well, not can change, but we can reassess the proportions of water that each of the countries put when they were thinking of dividing the water in this way, and how that has been either help to the overestimation, the overallocation, or not. I think this is an important issue. Think that, so this is mostly, not mostly, this is 100% water for the United States. Nonetheless, it was overestimated. Think that any of the tributaries was overestimated. People will be suspicious at why it was overestimated, and if so, what are the consequences? That's what we're doing. And that's what we're doing at this point. Okay. So, as we mentioned, this part will provide these kind of broader impacts. So, in this case, you can see here that with this natural flow regime, what we can do is associate, for instance, the rising limb or of the snowmelt to silvery minnow spawning. So we can use a lot of the information on these different locations and to understand how certain species, their life stage was attached to these specific flow events, and vice versa. The down limb of the snowmelt may have helped the leopard frog, the cottonwood, and so on. Also, we can see how this hurricane, monsoon-driven regime help also the matolete chato or other species that we know are important there. And these species, they are bioindicators. So having good habitat, having good conditions for this, they encompass the entire system, the entire ecosystem that depends on the river. Also, some of these flows help to shape the channels. In the Rio Grande, the river is highly influenced by, the river escape, the channel form is very influenced by the amount of water flowing in the river. So this is one of the impacts that this can have, or that I can see that the research that we're doing can help to inform some of these understanding of the freshwater ecosystems throughout the basin. Next, so let's, now we're going to be understanding drought patterns. Okay, so we have these 110 years of data in different locations. What we did is understand every year on every month, on every month, on the natural flow regime, we estimated if that given month the flow was either very, very slow or very dry, or if it was very wet. So basically, if any one of you have seen the PSI, the SPI, the Standard Precipitation Index. So basically what you do is every rain event you put it, if it is very wet, so more than 2 standard deviations, or if it is 1 standard deviation or 0.5 and so on. We did exactly the same with the flow. So basically we fitted the monthly flow through a normal distribution curve and get if the flow in a given month was plus half a standard deviation, plus 1, plus 1.5, as we're seeing here, and we characterize those as normal, wet, moderately wet, or extremely wet, or vice versa, dry, severe dry, extremely dry. Now, why is this important? What you're seeing here are those values compiled for 110 months, 120 months, so for 10 years. And what this tells you is that very early in a specific tributary of the river, what this tells us is that there were times during the early part of the 1900th century that they were very wet. So the flow that was occurring there was, when you compare it to the 110 years, it was extremely high. You can see that from the 1930s to the 1960s, mid-60s, there was a drought. Similarly, later we went back to an extreme period, a wet period, and then we went into a drought period. This is with the natural flow, with the estimated data that we calculated as natural. And here, this is the flow considering, no, this is the regulated flow. So if we use these standards, the standard or the standard of the natural flow, and we use that standard to associate that same value or a similar value to the dry to the observed flow, what you can see is that in any case, because we've been extracting water from the river and storing it, and the entire century was a drought. The entire century, when compared to the natural flow, how it was felt in the river, it was like if it was a drought. And if it was a very severe drought, a moderate drought, or a long drought. So that's what this tells us, that in this case, the river was swinging from wet to dry to drought to wet to drought periods. And in this has been a perennial drought. So that was for one of the tributaries. You can see here, in this case for San Marcial, so this is in the middle of New Mexico. This is in El Paso, so this will be in between New Mexico, Texas, and Mexico. And what you can see is that we have this kind of, well, here is Amistad, and here is Amistad is in just downstream of the Big Bend, and Anzalduas, it will be at the mouth of the river. What you can see here is that in San Marcial, the river has been actually in extremely dry conditions because of human alterations since the 1900s. In El Paso, the same. In Anzalduas, the same. And actually in here it's been since the 30s. So we had the river in a perennial drought. Not sure if you're aware, but the river currently is, there is no water in the Big Bend. There is no water flowing in the Big Bend. The river is dry. This will be, so this is on the main stem. This will be of the main tributaries. We talked about Salado. This will be San Juan, and so notice that in this upper area behaves differently than in San Juan when we have different timing for the wet seasons. This is the drought, but in any case, right now the system has been in a perennial drought. This will be a Ojinaga presidio for Conchos, and you can see that the river has been in dry periods and wet periods, but pretty much the observed flow, how it's felt in the river, is like if it was a continual drought. Similarly here, the Pecos Basin, a very wet period, very prolonged drought, and since then it's been a drought. So in this case, we're gonna publish this. We're on our way to write a manuscript and add some other things of resilience theory. Let me just taking a look at the clock. So this is the other side of the coin. So we have the 110 years of data. I explained droughts. Now allow me to explain flows. So Caroline, so how do you define what drought is in this context? Okay, so in this case, Caroline, what we did is the natural flow, we put it in, we use it, so that one will be our standard. We use the natural flow to understand the 110 years, did a distribution of those years and understand, make it in a normal distribution and see if those were +1 standard, +2 standard deviations, or +5, +1, +1.5, +2 standard deviations. So that means that they were, what were the years that fall into that category when we normalize, when we create a histogram of the flows. And we use that same parameter, that same range, that same value, that same magnitude to see how that value, in this case, how were -5, -1, -1.5 standard deviations. And most of them, they fall, most of the observed flow fall into that category, that if the observed flow would be, you can compare it to the natural, or you put it in the buckets of the different natural frequencies, beans, it will fall as they were in extremely dry or severely dry. Not sure if I explain myself well, Caroline, but it's basically looking at the natural flow, and that is our pattern, that is our template. And then when we look at the regulated flow, where does it fall in our template of the natural observations? Okay, so in this one, we went for characterizing floods. We estimate when did the peak flow occur, and also we did a flood frequency analysis, or magnitude and frequency analysis of windows of time every 20 years, and see how 10, 20, 50-year flood return period intervals, how they change because of wet years and dry years. So let me start explaining timing. What you're seeing here are those distributions. The blue ones are the distributions of the natural flow, and the red ones are the ones of the regulated. Now, typically we see these values, but we see them horizontal. This time we're seeing it vertical. So when we see kind of this hyetograph, these bars, we see them horizontally. This I'm putting it vertically, so we can compare both. So in Embudo, this is in New Mexico. You can see that because of the snowmelt season, they always occur between April to June, and so on. Some of them then later in San Marcial, Presidio, Rio Conchos, then they start, some of them they were influenced by, so the largest flow of a given year in this area, it was driven by the snowmelt. This is the snowmelt season. Here you can see that it was mostly snowmelt, but sometimes a hurricane will escape and go all the way north and produce the largest peak of that year. Here you can see that it is the opposite. Now, all of them, they are in this range, the natural occurrences. So what you're seeing is that these natural ones always occur during the hurricane season. Hurricanes were the ones that were creating these big flow events, the maximum flow event in a year. You can see that sometimes they came early, or that it was greater, the flow of the snow melt. So that's why we have this bimodal distribution. You can see here now that the regulated is all over the place. That's the timing. We have our species a little bit confused because we have peak flows all throughout the year. Here is actually the opposite. When in Presidio, when they used to occur here, now they are occurring in a different month of the year. Here you can see that their distribution is in some cases similar, in some cases different of the natural flow regime. So this will be in timing when the maximum, when the peak flows, the annual peak flows occur. And up, wait, there we go. Now, so this is so the annual peak flows. This is the 10-year. Okay, so what you're seeing behind is the maximum flow of these 10 years. And we did an analysis of windows of 20 years, and then we were moving the slide. So 1900, 1920, 1901, 1921, 1902, 1922. So the window was moving, and we estimate the 10-year flood. So the 10-year returning period of a given flood, and estimated what was the magnitude. So this is both. Tells you how often it occurs, the frequency every 10 years, and the magnitude. So you can see that natural flows way typically higher, way higher than in this case regulated flows. The flows that right now they are occurring, and many of them, I mean, during droughts, you can see that these flows will be lower. Also, you can see that the tendency, the flow, the direction of are reducing the 10 flow natural years. We have done this for, once again, for all the different parts of the basin. In this case, we have it for Embudo, Otowi, Orowi, Bridge, San Marcial, Presidio. And you can see how these ones are, these flows are definitely below what the natural occurrence of these were. You can see that the natural flows, for instance, in San Marcial, they always kept in this area. Right now, we have very few flows. The same in Presidio, the flows are almost zero, the maximum peak flows. This will be for some of the tributaries. So you can see here that the Rio Conchos, they were always here, the 1917 maximum peak flow. And you can see here that now the regulated are very low. And no wonder why we have this problem that the river is incised. And why is that? The river doesn't have the sediment, and the flows are very slow. These flows, if they will reset the channel, they will making it wide and shallow. And right now, because we don't have these flows, these large flows, the river is very narrow and incised. Okay, so basically here we are. This is where we are, and I do want to take some time for taking some questions or discussions. Let me just share with you one last work that we are doing outside of this project, but that I think is very interesting. So, resilience. So, we have those 110 years, and we have also the observed data. What we thought is, what if, even though there were certain uses of water, the river was still behaving, or it was still preserving some of the natural variability, some of the natural functions. So even though the system, even though the river was altered by irrigation, by reservoirs, the natural system was resilient. It has the capacity to absorb those shocks and still produce and still be producing these events. So that will be super cool, right? Because if we find parts that, even though there was human alteration, the river still was providing those functions, then we can estimate the carrying capacity of the river. We can estimate how much human development can occur, and that human development that occur still affects the basin. It sends shocks to the river, but the river can absorb those shocks and be resilient. Now, all of this, what I'm telling you, I mean, it is kind of intuitive that, yeah, sure, I mean, the rivers are resilient. They should be able to absorb shocks, and still some of them provide natural functions. Here, what we estimated, and this is work with Laura Garza, is when the river changed for a given regime that, yes, it was altered, but it was working, to a completely different regime that it's not anything like the natural flow regime. And with that date, we can analyze before how the river functioned, what was the human development. So that what I'm telling you, this is a proof of concept. So the blue line that you're seeing, well, so the first thing is that we have this Fisher index. So the Fisher index is used in resilience theory, and basically it analyzes time series data. And when it analyzes it, it tells you that the system is bouncing, but typically it stays between these plus or minus 2 standard deviations. This blue line tells you that, yes, there was a drought, but it didn't went out of the bounds. Here it went once and it came back. It pretty much is telling you that the river is absorbing shocks, climatic shocks, but it is still in the same flow regime. The regime persists, the ecosystem persists. Now, in this case, in the conscious, you can see that here we have the construction of a reservoir, Elephant Butte. And then here we have Irrigation District 05. And here we have the 1944 treaty. And in here, the construction of Francisco y Madero, one of the reservoirs. This black line is the Fisher index. This is the resilience metrics for, in this case, the observed data. At this point, the river changed into a different regime. It is different. It is completely different of the natural flow. This identifying when this happened, it can tell us or it can help us to understand before here. Yes, so what we call, or what we are naming, the royal we, Laura and I, a resilient flow regime. So what is a resilient flow regime? A regime that, yes, it's being exposed to shocks. In this case, those shocks are human development, but the flow regime persists. There is still providing natural functions. And then you can see that after this, then we're going to have other reservoirs, we're going to have other irrigation districts and so on. But the river was in a different state. This is something similar to the Pecos. The Pecos, you can see that it was again, the blue line is the variability, the large variability of the Pecos River in its natural form, and how it was sometimes really wet or really dry, but it was between these plus or minus 2 standard deviations. The black line is the regulated flow. And you can see that here there was irrigation district, they were 3 reservoirs, but until the Pecos River Compact, yeah, definitely that made the Pecos going into a different flow regime. These are the days when we actually broke the rivers, when we make them change into a different state. So anyway, first time that we're presenting this, this is very interesting because with this data from this side, given that we have the data, we can, and not only for natural or observed, we have also the water use data. We can estimate, and when it happened, we can estimate what is the carrying capacity. What is how much human development the river still can absorb and persist. So with that, I will leave it like that. So why is this important and many of these things? So let me just come back here. And in terms of actionable science, right? This line that you're seeing here, this red line, is how much water Mexico has to deliver from 1/3 of the flow of 6 tributaries. So Out of 6 tributaries, that 1/3, Mexico has to deliver this amount every the first year, second year, and so on. These lines are different treaty cycles, different periods where Mexico has been delivering water. Some of these times, there is so much water that there is no need to go to a 5th year, that in these cases, the reservoirs are full, and when the reservoirs get full, we start all over again a treaty cycle, a 5-year counting period. You can see that every time that we went 5 years, that there was no big hurricanes, no wet season, there was always a deficit to what it was supposed to be delivered, okay? In this one, we ended up here, or Mexico ended up here and then deliver water from the reservoirs. The current delivery of water for Mexico, so from 2020 to 2022, it is all the way below here. This is the first time, that we are so far away, so early in the time. This is the first time that Mexico is pretty much not delivering any water at all. It can be because of drought, it can be because of poor water management. But you can see that this is staggering. It's not a bottom line. This is where we are. With the information that we have, or that natural flows, we can pretty sure estimate what is the probability that we will end up here, or that the treaty will be reset because of a hurricane. We have 110 years of data, and we can play that probability game of what is the current trend, if we're going to end up all the way here, or what are the probabilities to finish here. So anyway, with that, I will stop there. Once again, thanking everyone for that that has helped out on these projects. Lau, Grace, Ramon, Gabby, Sam, myself. Anyway, thanks everyone. I'm happy to take any questions.